Today we are going to talk about power series. And to do that, we need to do a quick review of the ratio test, as that's going to be the focus of how we're going to solve power series. Although the root test may be used on some of the questions that you run into with power series, it's typically easiest to use the ratio test, so that's what we're going to focus on today. So for our quick review of the ratio test, remember that as the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n, if that limit is less than 1, then the series is considered to be absolutely convergent, and therefore the series is considered convergent. If that limit is greater than 1, or if the limit equals infinity, then the series is considered to be divergent. If the limit equals 1, the ratio test is considered inconclusive. That is, no conclusion can be drawn about the convergence or divergence of the series. So now that we've done the quick review of the ratio test, let's talk about what a power series is. A power series is a series of the form, the summation from 0 to infinity of c sub n times x to the nth power, where this would look like c sub 0 plus c sub 1 times x plus c sub 2 times x squared, and so forth, where x is a variable and the c sub n's are constants called coefficients of the series. So when you see this c sub n, that's actually a coefficient. And then when you see the x to the nth power, that's the variable. Now, for each fixed x, the series is a series of constants that we can test for convergence or divergence. A power series may converge for some values of x and diverge for other values of x. The sum of the series is a function, f of x, which equals c sub 0 plus c sub 1 times x plus c sub 2 times x squared plus all the way to c sub n times x to the nth power plus and goes to infinity, whose domain is the set of all x values for which the series converges. Notice that f resembles a polynomial. The only difference is that f has infinitely many terms. For instance, if we take c sub n equal to 1 for all n, the power series becomes the geometric series. It would become x to the nth power, which would equal 1 plus x squared plus x cubed plus so forth all the way to x to the nth power plus and would continue on to infinity, which converges when the x values are between -1 and 1 and diverges when the x values are greater than or equal to 1 or less than or equal to 1. In other words, when the absolute value of x is greater than or equal to 1. To give an example of each of these, a converging one and a diverging one, if we have our x value be a half in this geometric series, then we would get the convergent series from n equals 0 to infinity of 1/2 to the nth power, which would be 1 plus 1 is our c sub 0 term, plus 1/2 plus 1/4 plus 1/8, and you can see that each of these fractions are going to continuously get smaller and smaller, and so it would converge. But if we have an x value greater than or equal to 1 or less than or equal to -1, for example, x is equal to 2, which is greater than 1, we would get a divergent series, n equals 0 to infinity of 2 to the nth power, with our first term 1 for our c sub 0 plus 2 plus 4 plus 8 plus so forth. And as you can see, this series is going to continue to get larger and larger, and so therefore it would be divergent. More generally, a series of the form the sum from 0 to infinity of c sub n times x minus a to the nth power is basically another way of seeing a power series written. When it's written this way, it's called a power series in x minus a, or a power series centered at the value a, or a power series about a. Notice that in writing out the term corresponding to n equals 0, we have adopted the convention that x minus a to the 0th power equals 1, even when x equals a. So even when these two would subtract to 0, we still have the convention equaling 1. Notice also that when x equals a, all of the terms are 0 for n greater than or equal to 1, and so the power series always converges when x equals a. So now that we know what a power series is, again, basically it's our coefficient times a variable to some power, and you're going to see this series have a sum that either converges or diverges. We can try and see an example of this. And again, remember, we're going to really focus in on the ratio test for this, although sometimes you can use the root test. However, this one, because of the factorial, is a great one to use the ratio test with. Now, for example 1, it asks, for what values of x is the series from 0 to infinity of n factorial times x to the nth power convergent? So in this case, we're actually trying to determine the x values for which it's convergent, not necessarily whether it's going to converge or diverge. So we have to do a little bit of solving. And the question we need to ask ourselves, or the idea, I guess, we need to kind of follow, is in order for convergence to happen, we need the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n to be less than 1. And again, that's coming from our ratio test. So if we can get this to be true, then we can help determine for what values of x we would have convergence. So first, let's figure out what our a sub n and a sub n plus 1 expressions will be. So we have a sub n, which is what we're starting with, which is n factorial. This is just the plain sequence here. And then a sub n plus 1, anywhere you see an n, you're going to replace it with the expression n plus 1. So instead of n factorial, we'll have n plus 1 factorial, and instead of x to the nth power, we'll have to the n plus 1 power. Okay, so now that we know what our a sub n and a sub n plus 1 expressions are, we can now put those into our limit formula here to the right. So we're going to go ahead and write our limit as n approaches infinity of the absolute value, and then remember it's the a sub n plus 1 on top, so that's going to be n plus 1 factorial times x n plus 1 as our exponent over n factorial x to the n. Now, since we don't know what the x values are going to be, we do need to keep the absolute values on this. I know when doing the ratio test many times, we were able to drop the absolute values because we knew that it was always going to be positive. But in this case, we're actually trying to solve for specific x values, so you need to keep your absolute values on. So now we're going to use some of our algebraic tools to cancel some of the items in this ratio. And we can rewrite some of the factorial ideas and the power ideas so that things in the numerator and the denominator can cancel. So to start, remember that factorial simply means that you're multiplying by each number all the way down. So we would be multiplying n plus 1 times n times n minus 1, and so we can really just write that as n plus 1 times n factorial. And also, you can use the idea of powers to separate x to the nth times x to the first, because remember, when multiplying like bases, you would have added their exponents, which would have given us this expression over on the left here, x to the n plus 1. So we just separated our powers there. In the denominator, nothing really simplifies, so I'm just going to go ahead and write that again. But because we were able to use some algebraic manipulation, we're able to cancel things in the numerator and the denominator. So this n factorial will cancel, and this x to the nth power will cancel. And now we're left with the limit as n approaches infinity of the absolute value of n plus 1 times x to the first, or just x. Now, because the n plus 1 part of this limit is never going to be negative, since our n values are from 0 to infinity, we can actually take that n plus 1 part out of the absolute value and just keep the absolute value of x inside of the absolute value. Now that we've done that, we can actually take the limits separately using our limit idea. So the limit as n approaches infinity of n plus 1, that would approach infinity, right? Because infinity plus 1 would just be infinity. And so now we know the limit would equal infinity times our absolute value of x. Now, the ratio test says, so let me write this down, the ratio says that we need our limit, this L value, to be less than 1 in order for there to be convergence. So we need to ask ourselves the question, when is this infinity times the absolute value of x going to be less than 1? When is this going to happen? When is this going to be true? So we need to try to test some values for x. So let's think about this. When, let's say, if x equals 0. So if x were to equal 0, then the limit as n approaches infinity would have been infinity times 0, which would have been 0. So in this case, we would have had convergence. However, if x did not equal 0, for example, 1, 2, pi, anything, -2, the limit as n approaches infinity would have been infinity times the whatever number x was, which would have still been infinity. So that we would have had divergence. So these are the big ideas for when is this convergence going to happen. So in other words, when is our limit going to be less than 1? So we've basically found that if x equals 0, we'll have convergence. But at any other number, we will have divergence. Now, one thing that struck me is when I was working through this, I thought, well, isn't infinity times 0 in this x equals 0 case an indeterminate form? And it's actually not an indeterminate form because indeterminate of infinity times 0 means you have one factor approaching infinity, which we do, but the other factor would be approaching 0, which we don't. This x is not approaching 0. This case is different because we're saying that x actually is 0, not that it's approaching 0. So this means that no matter what the other factor is approaching, so whatever this other piece is approaching, this x is always going to be 0. And that's why this is not an indeterminate form, and it does, in fact, converge. So for our final answer, we would say the series converges only when x equals 0. So there is only one value of x that will make this convergent, and that x value is 0. Now, in just a few moments, we're going to talk about a slightly different way of writing the answers, but for now, this will work. Now, just as a review of the general ideas for our power series, here is our power series form, and there are only 3 possibilities for answers. In option 1, the series converges at one particular value when x equals a. So this is an example like the one we just did. So this is kind of like our prior example. Okay. The second option is when the series converges for all x values. This means all x values from negative infinity to infinity. And then finally, the third option is there is a positive number r such that the series converges if the absolute value of x minus a is less than r, and it diverges if the absolute value of x minus a is greater than r. So it converges if it's less than r. And then something to note is that r is considered your radius of convergence. So when you set up that inequality, that's going to be your radius of convergence. The interval of convergence of a power series is the interval that consists of all the x values for which the series converges. So in case A, when it's just one point, that interval would simply be just point A. In case 2, when the interval is when the series converges for all values from negative infinity to infinity, the interval would be from negative infinity to infinity. And then in case 3, the interval would be the inequality of the absolute value of x minus a is less than r, which can be rewritten like this. If this doesn't make immediate sense to you, just think of how you solve absolute value inequalities. They turn into compound inequalities. And then to solve this, you would need to add a to both sides, which would result in what we have here. So don't let this fancy form confuse you. All you're simply doing is finding the interval by solving the absolute value inequality. So when x is an endpoint, so once you solve this and you get your interval, there's going to be 2 values at each end, or excuse me, 1 value at each end, or 2 endpoints. Those values may be a part of the interval, and they may not be. So in some cases, you might find that the endpoints are not included. Maybe one of them is included, whether it be the first one or the last one, or maybe both of them are included. And again, this is all written in interval notation. So those parentheses mean they're not included, and the bracket means that they are included. Okay, so how do we find the interval for convergence? First, you're going to use that ratio test to find the formula for the interval of convergence. Then you'll set up that inequality to be less than 1. And again, the reason it's less than 1 is because of your ratio test. Okay, so it's going to be less than 1 for your ratio. Test. We know that it converges when your limit is less than 1. So what we would be looking for is your x minus a to be between -1 and 1. And then at this point, you would simply solve for x. Okay, once you have that interval, the next step is to check your endpoints to see whether they're going to be included or not included in that interval of convergence. And then you'll write that interval of convergence using interval notation. So let's see what this looks like with example 2. Now, example 2 states, for what values of x does the series from n equals 0 to infinity of x minus 3 to the nth power divided by n converge? So again, we're trying to find the x values for which this converges, but I'm highlighting this little piece right here for a reason, and that's telling us, if you notice the way in which our power series is written up here, x minus a is going to be the x minus 3 here, and so that is our center. That's telling us what we're centered at. So in this case, x minus 3 is telling us that we are centered at the x value 3. Because if I were to take the expression x minus 3 and solve that, set it equal to 0, x would equal 3, and so that would give us the value of 0. So x is equal to 3, so we are centered at 3. So the next thing we need to do is we need to determine what our a sub n and a sub n plus 1 little expressions are going to be. So a sub n is what we're starting with. So that's x minus 3 to the n over n. And a sub n plus 1 would be, again, anywhere you see the n plus 1, or excuse me, anywhere you see an n, you're going to put in an n plus 1. And again, we're doing this because we're trying out the ratio test. Okay, so that's why we're figuring out our a sub n and a sub n plus 1. So now let's put it into the ratio test. So now we have the limit as n approaches infinity. Again, you need those big absolute value bars. The n sub 1 goes up top. And then in the denominator, we have the original. And now we need to simplify. When you're doing this, when you're dividing by a fraction, it is best to try and simplify this doing the idea of multiplying by the reciprocal. So we will end up with x minus 3 to the n plus 1 over n plus 1 times, and the reciprocal would be n over x minus 3 to the n power. Now we're going to take a moment and simplify this a little bit using our power rules. So we're going to break apart some of these powers into pieces, which will help. So x minus 3 to the nth power times x minus 3 to the first power times n is in our numerator. So I took apart that n plus 1 power, and then I have n plus 1 times x minus 3 to the nth power. Now we can see that these two terms will cancel, and we will end up with the limit as n approaches infinity of the absolute value of x minus 3 times n over n plus 1. Now, because of the n over n plus 1, just like before, that part doesn't need the absolute value because that portion of it doesn't need to worry about being negative because our n values are always going to be positive. So I'm going to bring that part out in front. So we have n over n plus 1 times the absolute value of x minus 3. And so we'll look at each of these limits separately, kind of using the idea of that limit, some of our limit rules. So the limit of this first part is going to be 1. And the reason is the degree of your numerator and the degree of your denominator are equal, so we're taking the ratio of the coefficients. So degree of numerator is equal to the degree of your denominator. So we're taking the ratio of our coefficients. So now we just have 1 times the absolute value of x minus 3. And we know, according to our ratio test, that we need this to be less than 1. So we need to solve this for less than 1. And again, the reason is because we want that to be convergent. Okay, so there's our reasoning for it. And so now we're just going to set up our inequality. So we have 1 times the absolute value of x minus 3 is less than 1. And so I can divide over by that 1 in front of the absolute value. So really I just have the absolute value of x minus 3 is less than 1, which we all know is really negative 1. X minus 3, to get rid of those absolute value bars, is less than 1. And now we're just going to solve that by adding 3 to both sides. And so we would end up with 2 is less than x is less than 4. So basically what we have here is an interval, and from 2 to 4 we know there's going to be convergence, but we don't know whether the endpoints are going to be included or not included. We do know that we are centered at 3. And if you ever forget to find what you're centered between, you can take your two endpoints and just find the middle values. That would work too. So we know that it's going to converge between 2 and 4, but we need to check the endpoints. So let's kind of write that little note down. So we know convergence, or we know it converges between 2 and 4, but what about the endpoints? And that's what step 2 is talking about above, where it says you had to check the endpoints. So that's what we're going to do now. So starting with our original series, we're going to check at the x value 2, which is one of our endpoints. So this series is going to become from n equals 0 to infinity. If we were to take the x value 2 and plug it into our x, we would end up with a negative 1 to the nth power over n. And if you recall, this is our alternating harmonic series, which we've actually already talked about, and we actually already know that this converges. But just to kind of go through the alternating series test one more time, there are two pieces to it. Remember, the first piece is that you need to know whether it's decreasing. And yes, this would be decreasing. It's the b sub n that needs to decrease, which is our 1 over n. And yes, that is decreasing. And the second step of our alternating series test is the limit of that b sub n as n approaches infinity. And we do know that as n approaches infinity, that is equal to 0. So you needed the first term, or the first part of the test, to be decreasing, the second part to be 0. And because these two do have that happening, we know that it converges by the alternating series test. And because it's converging, this is telling us that the endpoint 2 is included. So up at 2, we can put a closed dot on our number line to determine that, or to say that we are including it. Now, let's talk about the endpoint x equals 4. Starting with our original series, if we were to plug a 4 in for the x value, we would end up with just 1 to the nth over n, which we can, of course, rewrite that as just a 1, because 1 to the nth power is just 1 always. And we know that this is a harmonic series. And by definition, a harmonic series always diverges. And so since this always diverges, we know that the endpoint 4 is not going to be included. So when we go up to our number line above, I'm going to put an open point on 4. So now that we have this little number line kind of drawn out, you can also actually see what your radius is. Your radius is the distance from the center to the endpoint. So our radius is going to be 1. So we have all of the information we need in order to write all 3 pieces of information for our answer. 1 talking about the radius, 2 talking about the interval of convergence, and then 3 talking about the center. So our interval of convergence is going to be the interval that we found. So in this case, it's going to include the number 2, so we would have a bracket, but not include the number 4, so we would have a parenthesis. Our center is what we described from the beginning. So this is going to be centered at x equals 3. And then finally, our radius of convergence is what we determined our radius to be. Again, we saw it on the number line, but you can also see a radius when you set up your inequality. It's what the inequality has it less than. So this would be the radius, in this case, is equal to 1. So there's our answer for example 2. And now on to example 3. This is going to be our last example for now. Example 3 says, for what values of x does the series from 0 to infinity of -1 to the nth power, x to the 2n power, over 2 to the 2n power times n factorial squared converge? Now, I just want to point out that you can tell that this is centered at, looking at that x value, since there's nothing being added or subtracted, we can say that this is centered at x equals 0. And we'll need that for part of our answer, potentially. Okay, so since we've been talking about the ratio test, that's what we're going to continue to use. So focusing in on the ratio test again. And this is a great one for that due to the factorial. We need to determine what our a sub n is, which is the sequence that's given to us, -1 to the n, x to the 2n, over 2 to the 2n, times n factorial squared. And then for a sub n plus 1, remember anywhere you see an n, we'll rewrite it as n plus 1. So we have -1 to the n plus 1 power times x, 2 times n plus 1, over 2 to the 2 times n plus 1, and then we have n plus 1 factorial being squared. Okay, so those are two pretty complicated math statements there, but we're going to put them into the absolute value as our limit approaches infinity, and then we will try to simplify as much as possible so that then we can take the limit. So what I've done is I've written it in the ratio test setup. So we have the a n sub 1 in the numerator and the a sub n in the denominator. And then all I did, because we have a fraction being divided by a fraction, you can take the denominator and do the reciprocal. So that's what I rewrote over here. So this is still my numerator to the left. So -1 to the n plus 1 times x to the 2 times n plus 1 over 2 to the 2n plus 1 times the n plus 1 factorial squared. And that is then being multiplied by the reciprocal of what was in the denominator, which was our a sub n. So the reciprocal of a sub n is 2 to the n times n factorial squared over -1 to the nth power times x to the 2n power. And so now that I have it like this, I'm going to try to rewrite this as best I can. So that's going to be equal to the limit as n approaches infinity. And with this, we're going to do a lot of breaking up of our powers here. So this first one here, this -1 to the n plus 1 power will become -1 to the n, and then -1 to the first, or just -1. So there's our first breakup. For our second one, we're going to break this up. You would need to distribute this little 2 here. So it'd be 2n plus 2. Okay, so we're going to break that up to be x to the 2n power times x to the second power. So that's that part of the numerator. Then we have this right-hand side of the numerator here. So we're going to write that, which the first one is just going to be 2 to the 2n, so that's not going to change. So times 2 to the 2n, but then we're going to multiply it by n factorial squared, which is just going to be n factorial times n factorial. So there's our numerator, very much expanded. And we're going to do the same idea with the denominator. So again, because of this 2 times n plus 1, we're going to have to distribute that 2 through. So it would be 2n plus 2 So when we break that up, it's going to be 2 to the 2n times 2 to the second. And then we have this n plus 1 factorial, which we can break up. We're going to break this up in two ways. The first way we're going to break it up, I'll do above. So this is actually going to break up into n plus 1 factorial times n plus 1 factorial. But then, so that I can, cancel with things in the numerator, I'm going to break that up into n plus 1 times n factorial. So that's actually going to break up twice. So this will become n plus 1 times n factorial. And same for this one. So n plus 1 n factorial. And that makes it so that I'm able to simplify things in both the numerator and the denominator. So there's my n plus 1 n factorial, and then a second n plus 1 n factorial. Okay, so I have that part. Then we have the negative 1 to the nth, which would just be as it is. And then we have x to the 2n, which would just be as it is. So this is all still in absolute values because I have those x values in there, so I'm not sure if the absolute values are really needed or not. So it's best to keep them. So now we're going to do some simplification, and anything that cancels in the numerator and the denominator, we're going to cross out. So I have a negative 1 to the nth that will cancel. I have an x to the 2n that will cancel. I have a 2 to the 2n that will cancel. I have an n factorial and another n factorial. Okay, so as you can see, we have a little bit remaining in the numerator and a little bit remaining in the denominator. So I've cleaned this up a little bit. What we had remaining was a negative 1 and an x squared in the numerator. We had an n squared, which is really just a 4 in the denominator, and then we had 2 n plus 1s, so that'd be n plus 1 squared. Now, you can get rid of absolute values for everything except, at first, the x squared, because typically we leave it around our variable. But because the x squared is being taken to the second power, right, it can never be negative. So the absolute values can actually drop on all of this. And so we're going to kind of write this as the multiplication of two pieces here. So we'll have our negative 1 fourth times 1 over n plus 1 to the second power times x squared. Now, what we can do is we can kind of think about, okay, well, this first part here, the limit of that, the denominator is going to continue to grow, the numerator would stay the same, so the limit of that is going to be equal to 0. So we would have 0 times x squared, and so we need to determine when is that going to be less than 1. And again, we're trying to determine why it's less than 1 because convergence happens when the limit is less than 1 according to the ratio test, and we're trying to determine for what x values is it going to converge. Now, because 0 times x squared would truly just be 0, then this is always going to be true because 0 is always going to be less than 1. So because this is always true, we're going to say that it converges for every x value, which in other words would be described as negative infinity to infinity. And so if you want to write it in the terms of the interval, the radius, and the center, we would simply say the interval would be from negative infinity to infinity. The radius would be infinity, since it doesn't really end, and it would be centered at what we determined at the beginning, which was 0. So this is the type 2 answer when it has all numbers for x working. So we've gone through examples when it's just, so example 1 was just a single point that would work, a single x value. Example 2 was when it had a particular range of values, and then example 3 was an example of when it would be all numbers. So that takes us to the end.